Today's video is about the principle of moments and applying that to problems. The first thing we need to know about is the center of gravity of an extended body. So this is the language that the specification uses. And basically this means that we need to be able to, for any object, identify where the center of gravity is. If it's a regularly shaped object, that is very straightforward. It is the point where all the axes of symmetry intersect, as you can see in the pictures here. And therefore, in this situation, if we were drawing a free body force diagram, we would draw an arrow from the center of gravity to show where the weight acts from. And that is the definition of what a center of gravity is. It's the point from which the weight of an object acts. And so no matter what the shape, as long as it's a regularly shaped object, we pretty much pick the center of it, and that is where we draw our force arrows. We do not need to find the center of gravity of an irregularly shaped object, but you should have an appreciation of where that center of gravity is. And we use the center of gravity in applying the principle of moments. The principle of moments says when an object is in equilibrium, the anti-clockwise moments are equal to the clockwise moments, or the sum of the anti-clockwise moments are equal to the sum of the clockwise moments if you have more than one moment. It also states that the forces, the vertical forces on an object, are equal. So in this example here, we have the normal contact force from the stick balancing out the weight of the object. So that's number one. And then any clockwise moment that might be caused by the weight of the stool on the right-hand side is going to be equal to any anti-clockwise moment caused by the weight that is hanging over on the left-hand side. And it is important to remember that both conditions must be met, that the moments have to balance, but also that the forces have to balance. Before we get into applying the principle of moments, it is worth looking at the different kinds of levers that are out there, the different kinds of problems that you're going to encounter. So this is a class 1 lever. It's the most straightforward type. The most important thing when you encounter these problems is to identify the pivot, because everything happens from the pivot. So as long as you identify where the object is balanced, or the turning point from which the sides will turn, this is a key principle here. And then after that, we're just looking at the forces that might be on the object that would cause it to turn about that pivot. So here we obviously have the force of the load downwards, and here we have the force of the effort on the other side. In order for this lever to be in equilibrium, then the force of the load times the distance of the load has got to be equal to the force of the effort times the distance of the effort from the pivot. So this is why the pivot is key, because all distances are measured from there. This is a very straightforward lever. This is like a seesaw, so I've given you that example there. There are plenty of others, but the pivot is between the effort and load, which makes it very straightforward to see. The class 2 lever is this one here. Again, step 1 should always be to identify your pivot, so that you can be sure you know exactly where you're supposed to measure from. And this time, our F1 is closer to the pivot than our F2. And you'll notice that they're in different directions because now they're on the same side of the pivot. And so it's really key to make sure that you identify which force would turn the object anti-clockwise and which force would cause the object to move clockwise around this pivot. So imagine that you're putting a pin in there where the pivot is, and this bar can move around that pin. So you're seeing then which direction each of these forces would cause the bar to move. And again, we do F1 times D1, if the object is in equilibrium, will be equal to F2 times D2. It is worth mentioning here again, and we will come to this in more detail later, that these distances must be perpendicular distances from the pivot. So you've got to make sure that they are running perpendicular to the load. So the force that's being applied is perpendicular to this distance from the pivot. And an example of a class 2 lever, as I've shown you down here, is a wheelbarrow. The third class lever switches those two. So there's your pivot again, and again, it's very important to identify that first. This time, our load is further away, so there's our F1, and this is our F2. And again, we're identifying F1 would tend to turn the lever clockwise, and F2 is the anti-clockwise force. And F2 times D1 in this case is equal to F1 times D2. This one is slightly more complex and tends to cause people more issues understanding it. So we're going to look at an example of this, and that is biceps. Now the labels in this diagram aren't entirely correct, but there is our pivot around the elbow. Our load will be the center of mass, center of gravity of your lower arm, which would probably occur somewhere down there. So that's the weight of the lower arm, and that would tend to move your arm clockwise. The effort occurs from your bicep pulling upwards. And so for this situation, your perpendicular distance from the effort is there, and the perpendicular distance from the load is there. And as long as you can identify those forces and those distances, then you can use the principle of moments and work out what those forces are or what those distances are. Now, all of that was covered at GCSE. The difference at A level is that our distances are not always perpendicular. And so we need to use our trigonometry to figure out what the perpendicular distances might be. And there are two ways to go about this, depending on what feels intuitively correct to you at the time. So suppose we have this situation. The box is not going to slide down here. It is fixed at the top, and we are trying to figure out what would be the clockwise moment of the weight of this box. So again, first thing we do is identify our pivot. If we focus on the blue arrows for the moment, this is the sort of method 1 that you can use. So if we know the weight of the box, that's our W force down that way. And we know the distance of the box up the slope here. The distance of the box up the slope cannot be used in this situation to find the moment, because we need our perpendicular distance that I've labeled D with a small subscript P here. We need the perpendicular distance from the pivot. So suppose our angle is 30 degrees, then we need to find out what this side of that distance is. And of course, the cos of 30 degrees would be adjacent over hypotenuse. So our adjacent distance, which is our perpendicular distance, would then be the hypotenuse cos 30. So the distance of the box up the slope times cos 30. That's method 1. If we now focus on the black arrows, method 2 is to find the force or component of the force, the weight in this situation, that is perpendicular to the pivot. So we're basically saying, okay, that is 30 degrees as well. Can I find the size of this force? And then it is perpendicular to the distance of the box up the slope. And we would use the same trigonometry here. We know that the cos of 30 will be equal to that adjacent side, which is WP in this situation, over the hypotenuse of that triangle, which is W. So our WP would be equal to the weight of the box times cos 30. And then to find the moment, you would multiply that by the actual distance of the box up the slope, because now, again, we have a perpendicular force to that distance. Two ways to go about it. Use the force that you're given, but find its perpendicular distance from the pivot, or find the perpendicular force to the distance that you're given. And some of these problems get quite complex, so I'm going to go through one such problem, probably the most difficult one that has come up in A-level physics so far. This one was actually on an AS paper, and I'm going to go through two parts of it, because we need the first part in order to do the second part, which is the main focus of this. But it's a portable basketball set, has a base and post. The base can be filled with water to increase stability. So there's our picture and our little blurb. The base has a capacity of 85 litres. Show that the maximum weight of the base is about 870 newtons if 1 litre is 1 kilogram, and the plastic part of the base has a mass of 3.5 kilograms. Step 1 is to say 85 litres times 1 kilogram per litre is going to be 85 kilograms. 85 times 9.81 to find the force for that is 833.85 newtons. So far so good. But of course, remember, we have to add on the weight of the base. So we're going to add on 3.5 times 9.81 because that's in kilograms. And so we end up with 868.2 newtons, which is approximately equal to 870. Let's look at what the second part has to bring to us. Due to the large area of the backboard, the basketball set may topple over when the wind blows. And this is the basketball set. At first glance, it looks very intimidating. The most important thing here is, first of all, identify where your pivot is, and it's right there. And then we want to try and take the context out and build ourselves force diagrams and moments diagrams for each of these forces. So let's have a look at the whole picture to start with. We have the weight of the base, and from the pivot, the weight of the base is the only thing that is offering us a clockwise moment. We have two forces that will offer us an anti-clockwise moment, the weight of the post and the force of the wind. The question asks us to calculate the minimum force of the wind that will cause the basketball set to be blown over when it's at the angle shown. Ignore the effect of the wind on the base, and they give us the weight of the post arrangement. The minimum force of the wind is going to be when the clockwise moment provided by the weight of the base is balanced with the anti-clockwise moment. So up to that point, it won't topple over, but after that point, after that perfect balance point, it will. So if we go ahead and find the clockwise and anti-clockwise moments and make them equal to each other, then we know that any more FW will cause it to topple over. And we need to break this down. So we need to start looking at our individual moments. So let's start with the clockwise one. We've got a little triangle here, and I'm going to draw this up here. Weight of base 0.45 meters is the distance of the center of mass, center of gravity of the base from the pivot. We know the weight of the base already because we calculated that above. 868.2 newtons. It's always a good idea to use your higher resolution number. Well, we need the perpendicular distance that weight is from this pivot. So we're looking for this side of the triangle here. And of course, we know this is 15 degrees because that's the angle of tilt. So the cos of 15 is going to be our perpendicular distance divided by the hypotenuse, which is 0.45 meters. Which means our perpendicular distance is 0.45 times cos 15, which gives us 0.435 meters. So now we have all the information that we need to find our clockwise moment. (868.2) multiplied by our perpendicular distance, 377.38 Newton meters. That is our only clockwise moment. So we're going to come back and use this number later on in order to balance out our anti-clockwise moments. Now, let's have a look at those. Breaking it down again, we've got the weight of the post, which comes down along here, and we have the distance of that post from the pivot, which is 2 meters. We know the weight of the post arrangement because they've given that to us in the question, that is 27 newtons. We know that at a tilt of 15 degrees, we want the perpendicular distance of this weight from the pivot. So let's go ahead and again draw a simplified diagram that we can use for this. There's the weight of the post, which is 27 newtons. This is our perpendicular distance. We know that this is 2 meters. We also know that this angle here is 15, which makes this angle here 75. Again, our weight of the post given to us in the question is 27 newtons. What is our perpendicular distance? Well, the cos of 75 is equal to our perpendicular distance, which is the adjacent side, over the hypotenuse, which is 2 meters. So our perpendicular distance is 2 times cos 75, which gives us 0.517 and change meters. Now we have both of the quantities we need to find this first anti-clockwise moment. So the moment is going to be the force, 27 newtons, times our perpendicular distance from the pivot, 0.517 meters, giving us a moment of 13.98 Newton meters. That is anti-clockwise moment A. What about the second anti-clockwise moment? If we go back up to our diagram, we have the force of the wind coming off in that direction. And we know that the total distance of that force from the pivot is 2.4 meters. Now in this case, I think it is actually easier to find the component of the force that is perpendicular to the pivot, rather than trying to find the perpendicular distance. Because again, we know that that angle in there is 15 degrees. So we want to find which part of that force, Fw, is perpendicular to this 2.4 meters. Then we can just use the 2.4 meters as our distance. Again, I'm going to draw a simplified diagram so that we can see this and easily calculate it. There's our pivot. That's our 2.4 meters. There's our Fw. This is the component of Fw that we want, with 15 degrees between them. So again, Fw is our hypotenuse, and this is our adjacent side. So the cos of 15 is going to be equal to the perpendicular version or component of Fw over the hypotenuse, which is Fw itself, which means our perpendicular component is going to be equal to Fw cos 15. And we know our distance from the pivot is 2.4 meters. So our second anti-clockwise moment here is 2.4 times our perpendicular force, which is Fw cos 15. Fw is what we're trying to find, the force of the wind. And we're going to find that by making our anti-clockwise moments equal to our clockwise moments. Our clockwise moment was 377.38. Anti-clockwise A, 13.98. Anti-clockwise B, 2.4 Fw cos 15. So we make those equal to each other. Our clockwise was 377.38. And that's going to be equal to the sum of our anti-clockwise moments, 13.98 for the first one, and 2.4 Fw cos 15. So we're going to take the 13.98 from the 377, giving us 363.4, and that's equal to 2.4 Fw cos 15. To find FW, we then divide 363.4 by 2.4 cos 15, and that gives us the value for FW of 156.8 newtons. That is the force that will just keep the basketball hoop balanced. Any more force than that, it's going to topple over. So they asked us for the minimum force that will cause it to topple over, and there it is. What have we learned from this question? First of all, although it is a high mark question, it is a lot of work for 5 marks. So you need to do it in about 7 minutes. Which means in order to do this in about 7 minutes, you need to be able to identify those forces, pick out those triangles, and get to work pretty quickly. And in order to do that, you have to practice. You need to find questions that test all of this trigonometry and the speed at which you can do it. Identifying them, calculating them, equating them. So get practicing.